A pleasant day, everyone. We are Group 3 from BSCE-2B, and we are here to report about viscosity of a fluid. And our report will be started by...
I'm Margie Diendo from BSCE-2B, and I'm here to discuss the definition of viscosity. Most fluids offer some resistance to motion, and we call this resistance viscosity. So most of the fluids, they are not the ideal one, and so they offer some resistance to the fluid motion. This resistance occurs when the different layers of the fluid moves relatively with each other. Viscosity arises when there is relative motion between layers of the fluid. More precisely, it measures the resistance of flow arising due to the internal friction between the fluid layers as they slip past one another in fluid flows. So when the fluid flows in the form of layers having different velocity, it tends to destroy the relative motion of the different layers of the fluid. And since it tends to destroy the relative motion of the layers, it causes to have an internal friction, and this internal friction is just like when the solid moves to the surface of the solid. Viscosity can also be thought of as a measure of fluid's thickness or its resistance to objects passing through it. Next slide. A fluid with large viscosity resists motion because its strong intermolecular forces give it a lot of internal friction, resisting the movement of layers past one another. So the higher viscous fluid, the stronger that it will resist the motion due to the intermolecular forces causing significant internal friction between the layers. So these intermolecular forces plays a role in viscosity. Having a stronger attraction between the molecules, it causes to strongly resist the motion. And since the attraction between the molecules is stronger, it has the greater internal friction. On the contrary, a fluid with low viscosity flows easily because its molecular makeup results in very little friction when it is in motion. So here it says that the higher the viscous the fluid, the stronger that it will resist the motions. While the less viscous fluid, it will flow easily. Gases also exhibit viscosity, but it is harder to notice in ordinary circumstances. So gases also have viscosity, but unlike in fluid, the viscosity in gases is less noticeable in everyday situations.
Hi, I'm Nathaniel Jerry J. Ferrer of BSCE-2B. Now I will be explaining the concept of viscosity. Viscosity denotes opposition to flow. The reciprocal of the viscosity is called the fluidity, a measure of the ease of flow. Viscosity may be thought of as an internal friction between the molecules. Such friction opposes the development of velocity. Now, to explain further of concept of viscosity, here we draw an incline, and let's just say we pour water. First fluid, we pour water, and the second fluid, we pour honey. So as you can see, water has a higher fluid rate, so when we pour water, it will easily flow in an incline. And when we pour the second fluid, as you can see, it will have a slower downtime, or it will not easily flow due that it has higher viscosity. Now to explain further, according to science, when two molecules, positive ion and negative ion, in molecules we have this called that there is a law of attraction between two molecules. Now if two molecules, a positive ion and negative ion, are closer to each other, they have more internal friction. And when another two molecules, another positive and negative ion, but this time it is greater apart or has a huge gap between them, it has a lower law of attraction, or it has a higher fluid rate. So and it has less internal friction. So in here, it has a higher internal friction and here has a lower internal friction. So in here, with the molecules that higher internal friction, this means that it has a higher fluid rate, viscosity, and these two molecules have a lower viscosity rate. So in here has a lower fluid rate, and this has a higher fluid rate. So yeah, that's all.
Also, hi, my name is Matt Versigunor from BSCE-2B, and I am here to continue the report about concepts of viscosity. First, what viscosity controls the liquid flow in such processes as spraying, injection molding, and surface coating. The unit of viscosity accordingly is Newton second per square meter. The viscosity of liquids decreases rapidly with an increase in temperature. For most liquids, such as water, oil, and many others, as they are heated, the kinetic energy of their molecules increases. This increase in kinetic energy causes the molecules to move rapidly and bump into each other more, so which results in the decrease of its viscosity. The opposite happens when a liquid, such as water, oil, and many others, is subjected to low temperature. Next is viscosity of gases increases with an increase in temperature. So, like the liquid, when a gas is heated, the kinetic energy of its molecules will increase. But this increase in kinetic energy will force the molecules of the gas to bump into each other more, which will create friction and will strengthen the intermolecular forces of the molecules of these gases. So that will result in an increase in result in an increase in viscosity of a gas when subjected in high temperature. But the opposite happens when it is subjected to low temperature.
Hi, I am Isaiah Angela D. Hamili from BSCE-2B. So I'm here to discuss about the viscosity types. There are two viscosity types, which is the dynamic viscosity and kinematic viscosity. So first is the dynamic viscosity. It is often denoted by the Greek letter mu, and it is a measure of a fluid's resistance to shear or flow at a given temperature. It is essentially how thick or sticky the fluid is. For example, honey has a higher dynamic viscosity than water. And the second type is the kinematic viscosity, which is often denoted by the Greek letter V. It is the ratio of dynamic viscosity to the density of fluid. So it describes how a fluid flows under the influence of gravity. It's often used when you want to know how fast a fluid will spread out in a specific area. So in simple terms, dynamic viscosity is about resistance to flow, and kinematic viscosity is about the rate of flow.
Hi, I'm Grady Ira E. Estrella. I'm from BSCE-2B. And since many are confused about the two types of viscosity measures, so we decided to have a table for us to have a better understanding about the significant differences between the kinematic and dynamic viscosity. So let's start with dynamic viscosity. Dynamic viscosity is also known as the absolute viscosity. It represents the viscous force of a fluid, and it has a symbol mu. So dynamic viscosity can be mathematically calculated as the ratio of shear stress over shear strain, and it is used when the viscous force in a fluid is dominant. So the density in dynamic viscosity is independent, and it has a unit Newton seconds per meter squared. So the higher the dynamic viscosity, the greater resistance a fluid flows. On the other hand, kinematic viscosity is also known as the diffusivity and momentum. It represents inertia as well as a viscous force in a fluid, and it has a symbol mu. So, kinematic viscosity can be mathematically calculated as the dynamic viscosity over the density, and it is used when inertia as well as the viscous force in a fluid is dominant. So, the density in a kinematic viscosity is dependent, and it has a unit a unit meters squared per seconds. So, the lower the kinematic viscosity, the more readily a fluid flows. So, in conclusion about this table, the more about this table, two viscosity measures can have the same dynamic viscosity but don't have the same kinematic viscosity because both of these viscosity measures have different densities. Next slide.
Hi, I'm Marleka, a friend from BSCE-2B. I'm here to discuss about the formula. Before that, we define shear stress over shear strain as a property of the material that we call shear modulus or modulus of rigidity. It is the linear relationship between the two is only true as long as the material is elastically deformed, not plastically. It is only true as long as we are looking at the linear deformation in a stress strain diagram. As we look in the figure, if we're pulling the top plate that has an area with a force, it can be calculated as the force over area, and its unit is Newton per meter squared. Also, the shear strain is equals to derivative of theta with respect to time. Its unit is 1 per second. And just like in solid material that is being elastically deformed, where the shear stress over the shear strain is a constant that is called shear modulus here in fluids, but specifically to Newtonian fluids. And also, shear stress over shear strain rate is also a constant that is called viscosity, and this viscosity is specifically to dynamic viscosity. And we will be using the mu as its variable, and also the unit of dynamic viscosity is in metric can be found by substituting Newton per meter squared over 1 per second and rearranging to either Pascal second or substituting kilogram over meter second. Since we will be using the density of the fluids from main calculations, this density of the fluids is next to dynamic viscosity. The formula of dynamic viscosity, as you can see, the shear stress is equals to mu multiplied by derivative of u over with respect to y. And also, we define the kinematic viscosity with the letter of mu is equals to dynamic viscosity over the density of the fluids. And by substituting the units of each kilogram per meter second over kilogram per meter cube, and it will turn out as the meter squared of per over second. And an easy way to remember the kinematic which motions, it should be similar to velocity, and its unit is meter per second. And in this case, there's just an extra meter on top.
I'm Jared Kenby's contact from BSCE-2B. I'm here to discuss the viscosity measurement. The elementary way of measuring viscosity is to allow a sphere, such as a metal ball, to drop to a fluid and time the fall of the metal ball. The slower the sphere falls, the greater the viscosity. But a more accurate measure of the viscosity is given by the viscometer. From this situation, we will try to get the density of the metal ball and the density of the fluid. So from here, we will get the viscosity of the fluid. So U-tube viscometer. U-tube viscometers are also known as glass capillary viscometers or the Oswald viscometer. A viscometer consists of two reservoir valves here and here in the capillary tube. In one arm of the U is the capillary. A vertical section of a precise narrow bore above is a valve. So, and with it is another valve lower down on the greater arm as shown in the image. So in use of the upper valve draws the liquid by suction, and then the liquid is made to flow down through the capillary to a lower valve. Two marks, one above and one below the upper valve, from C to D, indicate a known volume. The time taken for the liquid to pass between these marks is proportional to kinematic viscosity. The most commercial units are provided with a conversion factor. The time taken by the liquid to flow between 2 points is measured by multiplying the time measured by the factor of the viscometer. The kinematic viscosity is obtained.
So, I am Clear Spiller D from BSCE-2B, and I'm here to discuss the sample problem. A plate is 0.025 mm distant from a fixed plate, moves at 60 cm per second, and requires a force of 2 Newton per unit area, or 2 Newton per meter squared. To maintain this speed, determine the fluid viscosity between the plates. So, here's the given. dy, or the change in distance, is 0.25 mm. Change it to meters will become 0.025 times 10 to negative 3 meters. And the velocity of upper plate is 60 cm per second, and change it to meter per second will become 0.6 meter per second. And the force on the upper plate is 2.0 Newton per meter squared. So, using this equation, tau is equals to mu times change in velocity over change in distance, we can get our answer. And actually, it was explained earlier by Miss Laika, and she also has another formula, which is dynamic viscosity, or mu is equals to tau over du over dy, or change in velocity and change in distance, or can also be mu is equals to tau dy over du. So, by using our givens, we substitute our givens. So mu, our dynamic viscosity, is equals to our tau 2.0 Newton per meter squared times dy, or change in distance, 0.025 times 10 to the negative 3 meters over 0.6 meter per second. Cancel meters, and using our calculator, we're going to have an answer of 8.33 times 10 to negative 5 Newton second per meter squared. Converting it to poise, we will multiply it by 10 poise is equals 10 poise is equals to 1 Newton second per meter squared. Now we have 8.33 times 10 to negative 4 poise, and that's the answer. Thank you.
So we are the group 3 of BSCE-2B. That is our report for viscosity of a fluid.
Thank you.